Hey everyone, this is Daniel for Rock the JVM, and you are watching a comprehensive guide to structured concurrency in Java, which is a beast of a topic. So this video assumes that you have some foundations of Java virtual threads, for which we have some comprehensive guides, both in written form and in video form here on Rock the JVM and also on the blog. I'm going to leave links in the description of this video. If you want to make the best use of this video, I recommend that you run the code that I'm going to share. I'm going to share a GitHub repository that you can use to play with this code and experiment on your own to test the ideas that I'm going to show you in this video. Also, if you forget anything, just refer back to this video or to the written form at rockthejvm.com/articles. And the article here is on Rock the JVM. If you click on articles, you'll see here Project Loom Structured Concurrency in Java. My longtime collaborator and friend Ricardo Carden has created a beast of an article. This is the second biggest article on Rock the JVM at a whopping almost 1 hour of reading time, but it's probably going to take a little more if you want to experiment with this. And Ricardo went into really great detail describing pretty much everything there is to know about structured concurrency in Java. And my job in this video is to do justice to this article and demonstrate some similar code examples that Ricardo has shared. So as I mentioned, I'm having an IntelliJ project, a Java project, using Java 23, which was released in mid-September 2024. And structured concurrency in Java is at its third preview as of the moment of this recording. And in order to enable the structured concurrency API, here I'm going to add a compiler argument to -- enable preview in order to be able to use that particular API, even though it's in technically a preview state, and it could be changed at any moment. It's very doubtful that this API will be changed in the next LTS version of Java. So, what's structured concurrency about? Structured concurrency is a way of organizing the lifecycle of your concurrent computations. So, in general, we have many different forms of concurrent computation and of concurrent programming, starting from callbacks and futures, effect systems, reactive programming. There's a million different concurrency models out there. But structured concurrency's biggest goal is to be able to isolate and organize the life cycle, so the span of time during which you have concurrent code. And structured concurrency is hard, which is why I'm going to take the appropriate time to demonstrate it in this video. So for this example, I have a fictitious use case where we have a crawler of GitHub users and repositories. And under the domain package here, under the repository that I'm going to share in the link to the description, we have a domain where we have, for example, emails, GitHub users, repositories, various data structures described by Java records. And we also have some interfaces which describe capabilities in a standard hexagonal-like architecture. So, for example, in the ports and adapters style of organizing your code, we have these capabilities described by interfaces. If you're more into functional programming / mathematical thinking, this would be analogous to quote-unquote algebras. But in the hexagonal architecture, we have ports described by interfaces and implementations of these interfaces in the form of various services. So, for example, we have the capability to find a user by ID and the capability of finding repositories based on an existing user ID with this description that this particular API may throw some exceptions. Because as we will see later, exception handling is very, very important in concurrent programming, and it's one of the hardest problems in concurrent programming, which is why we have this structured concurrency model. Okay, so we have some definitions described by some interfaces. We also have a bunch of services. I'm going to walk you through them as we progress through the concepts. But in principle, we have an interface called find GitHub user. So we can obtain a GitHub user by a user ID and also fetch their repositories by these interfaces. And we also have a bunch of services that are already implemented. For example, this GitHub repository is a class that implements both of the ports that I described in the interfaces earlier. And the find user and find repositories are just fictitious functions that may in real life query the GitHub API, but just for this particular example, it takes a bit of time for the computation to return. It logs a bunch of stuff and it returns some data that are being hard-coded in this particular application so that it's easy for us to keep track of what's happening. So essentially, the find user and find repositories just takes a bit of time and then just returns some data structures. That's all it does. And these logs are important for us to see the progress of the application. And the static delay function may be imported by other classes via an import static statement. So this just does a thread sleep, which will work quite well in the realm of virtual threads. So this is just an implementation of these ports. It does some locally available data fetching, and it takes a bit of time for these functions to return. Okay, so this is the standard functionality that we have. Okay, now I want us to take a look at the first use case, or the first usage of this quote-unquote API, by looking at this sequential service. So find GitHub user sequential service. This is a description of the find GitHub user service. So this interface describes the capability of finding a user. And this find GitHub user sequential service essentially calls both of the APIs from the GitHub repository sequentially, one at a time. So this is just a basic constructor. The important thing is the find GitHub user by user ID, and this returns the GitHub user with the user ID and their repositories by calling the find user API first, waiting a bit of time, then finding the repositories, waiting a bit of time, and returning the GitHub user as requested. But as we can tell, finding the user and finding the repositories are two completely independent computations. They don't have any dependent data, so that we have to wait for the first API to finish before running the second one. Both of these can be run in parallel. So there's no need for us to run sequentially. We can parallelize them, especially if calling APIs takes a bit of time. Now, although this code is inefficient and in production it can actually be quite disastrous in terms of performance, it has a bunch of good features. For example, it has a clear scope, so these computations are clearly well defined. Their lifecycle is defined by the scope of this function. And the exception handling management is very straightforward because the interrupted exception and execution exception can be treated at the point where it happens. Now, let's see how this function works. Just to set a starting point. So here under Structured Concurrency Demo, this is the main entry point of the application. So public static void main with a bunch of loggers and whatever. We have the GitHub repository, which is the quote-unquote API. This sucker is the API that we're calling. And all calls to the functions will take a bit of time. Then we have the service described by the API, and we have new find GitHub user, and I'm going to start with the sequential service. So this is going to be sequential service, and I have to make this public. And if we call find GitHub user, it will take a bit of time. We run this application. So look at this. We have finding the GitHub user, user found, then finding repositories, repositories found, and then we're returning the GitHub user with all the repositories in sequence. This is nothing rocket science. There's nothing rocket science about it. Now, let's look at a concurrent version where we can parallelize these computations. So let me go to the concurrent service. Now, logger and the fields of this particular class are quite straightforward. This is the regular Java boilerplate. The important thing, the find GitHub user API, is returned by find user executor. Find user executor essentially calls the GitHub APIs, quote unquote APIs, by submitting the find user and find repositories calls to an executor service. So we have executors new virtual thread per task executor. So we're using virtual threads in this case. And we're submitting two tasks. And the user and repositories are going to be returned as futures. So this is a future of user and a future of a list of repositories. And the final value, the GitHub user with user.get and repositories.get, this returns only when both futures complete. This is a blocking call. All right, so this is going to block until both futures have a value. And after both futures have a value, then you can wrap up the data into this GitHub user. So I'm going to go back to my main application, and instead of the GitHub user sequential service, I'm going to use the concurrent service. And the find GitHub user concurrent service will start both computations in parallel, and it will wait for both of them to return. So look at this. We have finding user and finding repositories. Both features are spawned at this place. And then when both features complete, then we have the GitHub user with the appropriate data. So nothing rocket science so far either. Now, this probably seems nice and smooth, but problems start to arise when one of the APIs that we're using to find the GitHub user, so in this case, we're using in the concurrent service this sucker, if any one of these APIs throws some sort of error, then we have some resource leakage because, for example, if the find user function throws an error, then the find repositories is still going to proceed and it's going to waste resources or network connections or memory or simply CPU time in order for us to obtain the correct result, even though the first result threw an exception. So in the find user, let me go to the GitHub repository where the API happens here. Instead of returning a user, I'm simply going to throw something. So I'm going to say throw new runtime exception. So this is something that occurs at runtime, maybe a network glitch or anything else. I'm going to say, for example, I don't know, socket timeout. So in this case, where we have socket timeout, if we run the application one more time, let's run it one more time. Look at this. Both APIs are still being triggered. So finding user and finding repositories are both triggered. The application obviously stops, but the computation required to find repositories is still being performed. So this computation is still performed even though the first function threw an error. That should not be the case, especially if we have some dependent computations to obtain a final result. So for example, here in this concurrent service, if we take a look at these two functions, if any one of these calls throws an error, the other one should be canceled. For example, cancellation is a hard topic, and we're going to see how cancellation is possible in the scope of structured concurrency. Now, what is structured concurrency in general? So as I mentioned at the beginning of the video, structured concurrency is a construct or an idea that allows subtasks to have a limited life cycle. So if you remember what we did earlier in the sequential service, one advantage of the sequential service is that all this code had a very strict scope, a very strict life cycle, and a very strict ordering to these computations. Structured concurrency allows some sort of guarantees that mimic that sort of thing in the scope of parallelism. So let's look at this other API that is currently grayed out, find user scoped. So previously, we did executor submit where we called the find user and find repositories. Look at this other API. We're seeing a scope here. So we're doing a try with resources. And the variable that, or the resource that we're instantiating here is not an executor service, but it's called a structured task scope. There are multiple structured task scopes that we can instantiate. And the first structured task scope that I'm going to use is the plain one, new structured task scope, like this. The structured task scope is typed with the kind of value that you're returning after the scope has finished. So a scope is very similar in functionality to an executor service in the sense that you can spawn tasks. So the spawning of tasks is called forking, which is conceptually similar to submitting a thread to an executor service. So these are virtual threads. Okay, so structured task scope has the ability to fork new tasks which are going to be run on virtual threads. But conceptually, structured task scopes are limits to the life cycle of these tasks via the join functions. And I'm going to show you how the join functions work. So essentially what the join function does is a semantic blocking. And semantic blocking we discussed in the video of virtual threads. Semantic blocking means that no actual CPU thread or operating system thread is being blocked, but this simply waits until both or all tasks in this scope have results or exceptions. And then finally, at this point, we now know that all tasks will have results so that the get functions will simply return instantly. So let me show you how this thing works. I'm going to use this function find user scoped here under the main API. So find GitHub user is going to use this function now, not the old one, find user executor. Let me go back to my GitHub repository and let's not throw the exception for now. I'm going to return back to exceptions and see how exceptions will influence the lifecycle of structured scope tasks. Okay, so back to the normal functionality, and I'm going to go back to my main application and run this one more time. So look at this. We have two tasks that are being spawned in parallel, so they're spawned at the same time. We have values at different points in the future, and then after the log has been completed, we now know that both tasks have been completed, and so we're returning the final GitHub user. Okay, so this is very similar to what we did earlier with the executor service, but this API with forking and joining and the active management of tasks lifecycle is far more powerful and gives you fine-grained control. First of all, it is illegal to call get functions on tasks that are not known to have been completed yet. If it just so happens that at this point a task has been successfully completed, then you can call get, but it's not advisable to do so. The semantic block is mandatory before exiting the try resources. So if you don't call join, so let me comment this for a moment. So I'm not going to call scope.join. I'm going to call get, which may or may not return results based on the state of the tasks. But exiting the try with resources, so in other words, exiting the scope without having finished the tasks first, is an illegal state. So I'm going to run my application one more time and show you how that thing works. So let me run this one more time. So look at this. We have the tasks started, but then exiting the try with resources block gives me an illegal state exception saying owner did not join after forking subtasks. So the scoping API will essentially force you to finish your subtasks before exiting the scope, which is the entire purpose of structured concurrency. So structured concurrency, as a general principle, will not allow subtasks to outlive the parents. So subtasks do not outlive parents. So joining is mandatory. All right. So we have that clear. Now, let's get back to exceptions for a moment. So let's assume that the find user thing throws an exception. So I'm going to comment the normal functionality. Let me run the application one more time. And let's see how this thing works. So look at this. We have the tasks spawned in parallel. We have repositories found, but after the tasks have been successfully joined, so the tasks have been completed, but we don't know exactly what they've been completed with, we have result is unavailable or subtask did not complete successfully. In our case, we have the subtask which does not complete successfully. In other words, if a child task fails, the entire parent fails, or the entire scope fails. So another principle of structured concurrency is that if, or in the normal case, so the default case, is that if a child dies, or if a child throws an exception, the entire scope fails. This is the word that I was using, failure. So if a child fails, the entire scope will fail. Now, we can manage this default case, or we can change the behavior of the entire scope. So we can say structure task scope dot shutdown on failure or shutdown on success to cancel the remaining tasks. So we can control. So if a child fails, we can say whether we want to cancel other tasks, which is important. So maybe you don't want to cancel the other tasks. Maybe the tasks are independent. Maybe you want to send an email or something, and you don't want to cancel that email being sent. But for example, for dependent computations, you might want to cancel other tasks for resource starvation, which seems to be our case, for example. So I can manage the structured task scope by saying new structured task scope dot, and there are two ways of shutting down when you have a result or shutting down when you have a failure. So I'm going to say structured task scope shutdown on failure. So if we have a shutdown on failure task scope, when we're joining and one of the tasks throws an error, the other one is being canceled. So shutdown on failure means if a child dies or fails, the running tasks are canceled. And cancellation with virtual threads is still being done via thread.interrupt. We talked about that in the virtual threads video. In other words, Let's see how this is going to work. So we saw earlier, look at this. So in the previous run, we had finding user and finding repositories. And then before the scope failed, we did have the successful task printing out the result. So repositories found for user ID. Remember this output because I'm going to run this one more time. So I'm going to run this. And look at this. We have the tasks being spawned. We have both fork tasks completed, but the running task was failed at the moment the first exception was detected. So the repositories API call, which was the successful one, was canceled. There's no other print being shown here in the console because the finding of repositories is canceled. If we take a look at the concurrent service, this sucker fails, the first one, so fails. This other one should have printed something, so should have printed in the case of success, but is being canceled because the first one failed. All right. So if we are using shutdown on failure, we can essentially control which tasks are being canceled and which are not by choosing the appropriate structured scope. Now, obviously, in the case of success, this shutdown on failure will produce the exact same result as the previous one if everything goes on the happy path. So if no subtask throws an error, then this particular structured scope will simply proceed as normal. So this is a way that we can avoid thread leakage. But if you take a look at the exception that was being thrown, it says illegal state exception. Result is unavailable or subtask did not complete successfully. Which subtask did not complete successfully? What was the error? What was the cause of this? We don't have any sort of reasoning why this illegal state exception occurred. So we lost the cause of this particular state. So we can change that, and the shutdown on failure scope has this extra capability in a sort of a builder-like pattern to say scope.join dot, and there is a function called throw if failed. And throw if failed essentially throws the original exception that was being thrown if something went wrong. So this throws the original exception. So if I run the application one more time, look at this. We have the execution exception, which is the runtime exception, which is the socket timeout, which is the original cause of the failure. And also then we have the execution exception and the stack trace that can track where the exception occurred. So with this API, with throw if failed, you can essentially control which exception you want to throw, the exception of the scope or the original exception. Even more than this, you can control what kind of exception you want to throw. So you can control what kind of exception to treat and what kind of exception to throw later. Because the throw if failed function has two overloads, one which looks like this and one which takes a lambda. So throw if failed, look at this, we have a function from throwable to something which can return a different kind of exception. Okay, so you can say throw if failed, for example, you can say throwable or T arrow, and then you can treat this exception to say if T instance of exception, maybe handle this exception, so you can handle the exception here. Okay, let me open some curly braces here because I want to be in Java, and Java has lots of curly braces. All right, so T says if T instance of exception, otherwise else throw maybe T. And because T is a throwable and the Java type system doesn't catch this, this is going to be an error. So I can wrap this. Okay. So T says if T instance of exception, handle the exception here, otherwise throw T. So if T instance of exception, you can do something like log info. So I can say logger, let's say error, say exception here, and then return T. So the function that you supply to throw if failed will return a new throwable, which is going to be thrown later. So this can process the exception and return or throw the resulting exception. Now, Java still mandates this throwable thing because I'm returning the T, which throws throwable, which needs to be caught, which needs to be managed and mentioned here in the method signature, which is why I'm going to comment this all together just for you to have the explanations there. So I'm simply going to say scope, join, and then throw if failed. That's it. Okay. So scope.join.throw if failed will essentially allow you to handle the original cause and throw a processed error later if you want, which means that you can control what kind of exceptions gets thrown in the case that one of the tasks fails. All right, so I hope this makes sense. We can shut down on failure to manage the thread leakage and the cancellation of tasks that have not been completed yet in the case that one of the tasks has failed. Now, shutdown on failure is one of the two alternative structured task scopes besides the default one. The other one is called shutdown on success, which completely finishes the scope in the case that one of the tasks has succeeded. Obviously, this case doesn't make sense for shutdown on success, and that's because if you complete the scope at the point where the first task is successful, the rest of the tasks will be canceled or will be stopped, and we want all the tasks to be successful at that stage. But we have a different example and a different use case to demonstrate that sort of feature, and that's an example of caching. So let's take a look at this find repositories by user ID cache. So this find repositories by user ID cache essentially has an in-memory map that is going to return an individual result if it is in the cache, or otherwise it will simulate a long network call, and then it will put it in the cache. So this particular example, the find repositories by user ID cache, essentially puts a hard-coded value here with a repository, Rock the JVM GitHub IO. This is the repository of my old blog. So this is going to be a fictitious cache, or maybe something like Redis, or something that you can use in production. Obviously, this is going to be an example that you can sift through very easily. So find repositories is simply going to look in the cache. If you don't have anything, it will log something, and so on and so forth. Adding to cache is going to simply add something into the mutable map. So there's nothing rocket science about this particular implementation, the find repositories by user ID cache. Okay. Now, there is an example of GitHub repository which uses this particular cache. So if you get to GitHub cached repository, it has a very similar structure to the old GitHub repository, which stores the old API. Okay. And the find repositories function, this is the one that we're interested in for this particular example. We have two tasks here. The first task is going to try to find into the cache. Obviously, this one is fast. And the other task is going to be scope.fork, and then it will simply resort to the old API. So call the old API, and if you found something in the old API, then I'm going to add to cache. So put it in the cache if you fetch something, and then obviously return the final result. So this is a standard mechanism which is meant to say something like find it in the cache. If not in the cache, call the old API and put it in the cache. But why wait? Why try to find in the cache and then, if not in the cache, call the old API? Just call the old API. So screw that. I'm going to say find it in the cache, find it in the old API, or call the old API. And I'm relying on the fact that the cache is super fast. So when the cache finishes, if the cache gets you something, cancel the other one. This is what this structured task scope shutdown on success is going to do. The first task that is going to be successful is going to finish up the scope, and by finishing the scope, it will finish all the remaining running tasks. Obviously, because the cache is going to be super fast, if it finds something, then the other task is going to get canceled, which is a good use of resources. And that's because we use the maximum resources only for the duration that we're interested in them, and we're canceling everything that we're not using the moment we have something that is useful to us. All right, let's try this out. So here under main, I'm going to take this sucker out. I'm going to have a public or a static void demo concurrency, and I'm going to simply say service find GitHub user whatever throws. I'm going to add the appropriate throws clauses, and I'm also going to have a static void demo success closing or closure. And I'm going to have this GitHub repository, which is the old API. This is the old API. Then I'm going to have the cache. So I'm going to say final find repository by ID cache, I think it's called. Okay, so this is cache as new whatever. Find whatever cache. And then I'm going to have a final find repository by user ID port. This is going to be GitHub fetch with cache. This is going to be new GitHub cached user repository, a cached version of it. And we have a GitHub cache repository here. So new GitHub cache repository with GitHub repository and this cache thing. Okay. GitHub cache repository, make it public. Okay, cool. And then I'm going to have my list of repositories, which is the function that I just demonstrated. So I'm going to have final list of repository. This is going to be repos as this GitHub fetch dot find repositories for the user ID. And I think the user ID is going to be 1 or something like that. Where's the cache? This sucker says list of user ID 42. Let's try with something that does not belong in the cache. So I'm going to say user ID, so new user ID with 1, like this. And I'm going to import list, GitHub fetch, find repositories. Okay, this probably throws. So I'm going to add the throws to the a method signature, and then I'm going to have my logger info. So I'm going to say logger info. I'm going to say GitHub repos for user, and this is going to be my user ID. So let me put this in a variable. So final user ID. Okay, user ID. Sorry for the Java boilerplate. I'm used to writing Scala a lot. I'm going to have my user ID, and then I'm going to have my user, and have my user ID. Okay, finally. Okay, let me put this in main. So this demo success closure I'm going to call. All right, and this demo success closure essentially tries to find the repositories of so GitHub user repos for user whatever. I'm going to have my repos here. Cool. So what I'm trying to do is I'm going to try to use the cache for a user that does not belong in the cache. So the cache that we have just demonstrated has by default in the constructor a user that has the ID 42 with a bunch of repos with Rock the JVM GitHub IO. I'm trying to find the repos for a user ID that does not belong in the cache. Essentially, I'm going to have the cache failing, and it's going to use the old API, essentially. So let me try to run this application. Let's see what we got. Okay, so look at this. We have finding repositories for user ID values equal 1, saying no cache repositories found for user ID value 1, which is okay. Repositories found for user ID, this is the old API, and then we have the whatever value the old API returns. And by the way, we need to have some sort of value that the old API can return values for. So the GitHub repositories has a bunch of things. For example, raise4s and sus4s. These are Ricardo's 2 repositories. So find repositories for any user ID is going to return these 2, which is what we see in the final application. All right. Now, let's try with user ID that exists in the cache. So 42L, which we saw earlier that exists in the cache. In this case, the cache will return very quickly, and the old API is not going to be triggered at all. So look at this. Finding repositories, GitHub repos found. Look at this. We have Rock the JVM GitHub IO. This was fetched directly from the cache, and the other one was not even triggered. So the lesson here is that the shutdown on success, where is that? GitHub cache repositories. This shutdown on success will finish up the scope and cancel all the remaining tasks if one of them finishes up with a successful value. This is useful for releasing resources that are left hanging. Obviously, this shutdown on success may also throw an exception if all the tasks fail. So for example, if the find repositories cache and the find repositories for the old API both throw an exception, then this shutdown on success scope will surface the first one that occurs. One other thing that I wanted to show you here in terms of, let's say, API, we have scope.join, which you saw earlier, but we also have the construct.result. In the previous case with the shutdown on failure, we had throw if failed. In this case, we have scope.join.result to be able to fetch the first result that was returned after joining the scope, which means finishing up the first task that returned a successful value. Now, just like throw if failed earlier, the result function can also take a lambda from the throwable that might have occurred by failing all the tasks. And you can say t, which is a throwable, and then you can, map the throwable to something else you want to throw if everyone fails. Okay, and the throwable that will be passed here is going to be the first exception of the first finished task. Okay, so I'm actually going to remove this and so that the code can compile. So I'm going to add a little comment here. You can also, and I'm going to have map the throwable to something else if you want to throw if everyone fails by saying scope.join.result by t to some other exception. This is just for you to have a little note when you browse the code. All right. So we have structured task scope, we have shutdown on failure, and shutdown on success with different mechanics. Now, the final thing that I wanted to show you in this already long and comprehensive video is how to define your own structured task scope, which is why I have here in the policy a very shorthand implementation of shutdown on result, which is built into the structured API of the JDK, but I wanted to show you how you would implement your own. So shutdown on result is a custom structured task scope that we implemented for this video. Ignore the implementation for now, ignore the functions. The only thing that you have to override is this handle complete function. Everything else is optional. Okay, so I can comment out everything and the code will still compile. The only one that you do have to override is this handle complete function. And the handle complete essentially controls how a subtask is going to be finished. So let me uncomment the rest of the code. And you can also override the join function if you want. The structured task scope is an interface with many methods that you can override. These are the two that I guess are going to be the most appropriate to override in the case that you want to implement your own structured task scope. Now, how would we implement a shutdown on result task scope? Well, in this case, if you remember, a shutdown on result essentially closes the scope when we get the first result, which is why I have these variables, first result and first exception, just to be able to surface out the first exception if all tasks failed, and surface out the first result if I get a subtask that has successfully completed. So let's look at the handle complete function. So the subtask API gives me access to the state of the subtask. So at the moment when handle complete is being called, the subtask can be interrogated for its state, and it can be in failed, success, or unavailable. So neither case, neither success nor failed, it's probably running. And I'm using a reentrant block here just to be able to synchronize on these variables for concurrent access, because if we use synchronized blocks, and due to the fact that the handle complete is being called from a virtual thread, that will essentially pin the virtual thread to an operating system thread. At the time of this recording, synchronized blocks in Java will essentially pin the virtual threads to the carrier threads or the operating system threads. That's probably going to change in future JDKs, but at the moment, this is the way that things are, which is why I'm using this reentrant block instead of regular synchronized blocks. All right. So let me check the subtask state. If it's failed, well, in this case, if I get a failure, I need to check the first exception. If it's null or not, I need to set that to the first exception that has been made known to me, which is what I'm doing here in this try catch. And I'm going to unlock for all other tasks to be able to handle complete. So whenever a task is finished with a success or failure, is going to call this handle complete function from the structured scope. Okay, so in the case of failure, essentially what I'm doing is I'm setting the first exception if I don't have it already. If I get a success, I'm going to do the exact same thing. So if the first result doesn't exist yet, then the first result is going to be the get function from the subtask. So the subtask has a result at this point. In both cases, I'm going to call shutdown. Now, this is not necessarily the logic for shutdown on result to wait for all tasks to finish and get the first result. So in the first result, I should do the shutdown, but this one is an easier implementation that will also surface the first exception that is going to be thrown first. So in case for success, I'm essentially doing the same thing as the case for failure, only that I'm treating the first result instead of the first exception. And in case we get unavailable, then I'm going to call the super method handle complete for the subtask and letting that deal with the JVM subtask as it sees fit. Okay, so this is the handle complete. Now, the act of joining is going to return an item of the same type. So I'm going to say super join and return this. This is essentially calling the super method. And result or throw, this is simply going to give me back the first exception if I have it. Otherwise, I'm going to return the first result. That's essentially it. So the implementation isn't really rocket science, but you can have arbitrarily complex shutdown policies or structured task scope policies depending on the use case that you have. So the structured API gives you the capability of controlling subtasks at a very low level. Now, let me see how this thing can work in a realistic use case. So here under service, we have a final thing that I wanted to show you. Find repositories by user ID with timeout. So timeout is a very common pattern with concurrent tasks. And I'm going to make this a public class. And let's read the code. So we have the delegate, which essentially calls a delegated API. And obviously, the constructor does exactly the same thing. Find repositories. Let's look at this particular method. We have the scope, which is my new shutdown on result with list of repositories. So remember, this is my own policy here. It's not a standard JDK thing. If I want to enforce some strict requirements for some SLAs for this particular API, for example, if this find repositories thing, if the old API takes too long, I can also fork a task that throws an exception, and if the exception has been thrown, that this will finish the entire scope, and this timeout exception will be the cause for failure and the cause for the shutdown of this custom policy. All right, so we have scope, join, result, or throw, and we can also use this in main. So let me go to structured concurrency demo, and let me do a static void demo timeout. And then I'm going to throw the same kind of exceptions. I don't even care if they're being thrown. All right, so I'm going to have my Git repository. This is the old API. Then I'm going to have a final find repositories by user ID with timeout. This is going to be find repositories, whatever. New find repositories with timeout. And the old API is the GitHub repository. Okay, so this is the delegated API. What? Yes, the constructor is public now. All right, cool. So, all right. We have this new API. Then I'm going to call the list of repos. So list of repos, I'm going to say this sucker find repositories with user ID, and the user ID is user ID with 1L or whatever. And this find repositories takes two parameters, the user ID and the timeout. So this is going to be duration. So this is going to be find repositories by whatever, find repositories with user ID, and let me add a duration. So I'm going to say duration of millis, and let me have like 200 millis. If I remember correctly, the old GitHub repository API for find user has a duration of 500, and I'm going to keep the old implementation. Okay. Find repository is not public. Yes, I'm going to make public, and I'm going to have my logger info, GitHub repos for user. Okay. So what this does is that I'm essentially calling the GitHub repositories find repos API, and then I'm also going to fork a new virtual thread that waits for 200 milliseconds, then throws an exception. Because I'm using my custom policy, that custom policy is going to finish at this timeout because this timeout is shorter. So this demo timeout, I'm going to call. Similar log messages. Yes, I don't care about that. So look at this. We have execution exception, and then we have this timeout exception. Timeout of PT 0.2s. So this is a timeout of 0.2 seconds. Has been reached. So you can implement your own custom policies for different use cases. And I've just demonstrated our own custom policy to shut down on result or exception with a realistic pattern, which is timing out or SLAing an existing API. So that's all I have for this video, folks. I recommend you check out Ricardo's article on structured concurrency in Java. It's really, really comprehensive with all the examples that I've demonstrated in this video. Structured concurrency is a hard thing, and Java is making some steps in improving the APIs and the control that it offers you in terms of managing the life cycles of your concurrent computations. So as always, I hope you liked this video. If you did, go ahead and click the like button and subscribe to the Rock the JVM channels for more videos like this. And check out the Rock the JVM website and courses for literally hundreds of hours of pretty much everything about Java, Scala, Kotlin, big data, distributed systems, and pretty much everything in between on the Rock the JVM website. Until next time, folks, this is Daniel signing off.